Hi, can you see me?
Yes. All good here.
All right, cool. Let's go.
All right.
Cool. I'm here.
Good morning, everyone. My name is Sunji, and we'd like to talk to you about our Wireguard Tunnel Manager project with Cisco Umbrella. Before we launch straight into things, though, let's just have a quick intro with the rest of the team.
I'm Cameron.
I'm Sinclair.
I'm Sunji. You heard from me earlier.
I'm Kylus.
I'm Jonathan.
And our sponsor for this project is Cisco Umbrella. It's Cisco's cloud security sector, and they specialize in everything from threat intelligence to cloud firewall solutions of organizations of varying size. Let's just talk a little bit about the internet today. The internet today is a valuable medium, as I'm sure you and I can agree. Especially in today's COVID world, we see it's something that connects us, allows students like ourselves to educate us, and allow engineers like you and me to build services that matter to users. With devices getting smaller and a lot more common in the form of smartphones, and information mobilizing faster and faster between these devices, there comes an immense amount of danger online.
One quick second. I'm using the wrong.
Yeah.
The wrong deck.
Oh yeah, all right. So we gave this presentation to Cisco as well. So
Yeah. I'm incredibly sorry about that.
nice.
1 second. Sorry for the delay. Here we go.
So we left off talking about how the internet is not completely secure. And the issue is that around 25% of the top 100,000 websites still don't use common cryptographic implementations such as HTTPS, with about 10% of all these sites supporting some weak or broken cryptographic implementation that just completely invalidates their security. Even company internal communications where nothing hits the web and everything stays on a company's intranet are very susceptible to snooping nowadays, with more and more companies moving towards a cloud solution for their connected services. So it makes even more sense to secure these connections. Some common threats that we see online: DDoS, where you overwhelm a target with weird traffic; man in the middle, where someone listens on the wire for traffic; and phishing attacks are just the most common forms of cybersecurity attacks on the internet, and they cause up to an average of $3 to $6 trillion in damages per year, which is a devastating loss. Some or all of these attacks are carried on in-flight data that we assume to be relatively secure already. And we have a solution for this. The easiest way to secure our data over the web is to create a secure encrypted tunnel from your network to another, such that an attacker anywhere along the way can read any data or trace where the real destination for a request is. Essentially, you'll pass your web traffic through to another computer that will make the request and receive the request for you. This technique of creating a virtual private network is the most popular way for companies and end users to secure their data. IPsec and OpenVPN are two of the most popular protocols in providing this service to personal users and companies. However, there are newer VPN protocols that are promising better speed, security, and even user setup. Enter Wireguard. So Wireguard is a new complete tunneling solution built with the extremely fast UDP transport protocol and very secure cryptographic key exchanges. There was only 4,000 lines of code in the first version compared to the hundreds of thousands in other protocols, which means you could read the code over your morning coffee. The advent of languages such as Rust, which prevents loss of memory errors typical of security issues, and fast key exchanges allow Wireguard to be both fast to use and fast to develop with.
When people have to connect to remote sessions, manually configuring the settings and setting up the connection can quickly become an annoying and tedious task. The key to solving this is a simple modern connection manager, which manages the communication between the client and the server. When the client makes a connection request, the connection manager redirects the connection to the server through the WireGuard interface. Our current architecture can handle multiple simultaneous users on a single server with their own isolated user space. Users can be authorized to use specific servers based on the user credentials or be routed to one of several different servers. This makes connecting remotely through WireGuard quick and easy for any clients. Cisco's goal with this project is to test whether WireGuard can be integrated with their infrastructure, if it's worth investing time into. Although Cisco gave us a great deal of freedom in designing this new project, our focus was a microsystem that would integrate with their service.
So over the course of our project, we made many difficult design decisions about which technologies to use. Golang and Rust are both powerful modern languages that we felt were equally worthy of consideration in developing our project, but in the end we decided to go with Golang due to its noticeably smaller learning curve, as well as the fact that it was already in use by our sponsors in their production environment. Containers provided an easy way for us to isolate and package code along with its environment, and multiple containers can be run on the same server. This is very important for our project as it improves the ease of setup and security. We chose to use Docker because it's a standard in the industry for containerization, and the abstraction it provides made it much easier for us to navigate the complex Linux networking and setting up IP tables necessary for routing traffic between our servers. At the beginning of development, we also used Redis due to its speed at data storage and retrieval. However, as we began to broaden our slice and develop a user verification system, we determined we would need to use a database with proven consistency and switched to using MongoDB. So now that we've explained a bit of motivation behind our project, as well as some of the technologies we used to build it, let's look a little bit more in depth at how it actually works.
So this is a small diagram kind of the flow of time and what's kind of going on in each component. We have the client device, the connection manager, and the WireGuard server. When a new client makes a request to our connection manager, they'll provide the necessary user credentials to recognize them in the database. The connection manager will then create a public and private key for this client and determine which server it will be routed to. And afterwards, it will then send that information, specifically the public key, to the WireGuard server of choice. The WireGuard server of choice will then use this information, get its own public and private key for its own server, and then create its WireGuard instance before sending that information back. This information will then be packaged in the connection manager along with the private key and public key of the user's WireGuard keys and returns it back to the client, who will then use that information to create his configuration file and add the server as a peer, allowing them to make a handshake right after and connecting each other as a new peer. WireGuard uses their own WireGuard public and private keys that are shared between client and server to authorize as peers on the server's WireGuard interface. We create our server and client keys on a per session basis. Every connection will generate a new key for both interfaces. Each user will have their own WireGuard interface that won't be shared with other users on the server. To provide this, we ensure an isolated environment for each user. This is where Docker really shines. Each WireGuard interface is spun up in a Docker container, and all packets that a user will send to the server upon connecting will be routed onto the correct container based on the IP table set after Docker is spun up. WireGuard has a key rotation system that is generated in pulses every few minutes. A new handshake is initiated that provides both the server and the client a set of rotating keys. We use this info to allow us to know when you are still actively connecting to our interface to determine when we should remove you as a peer. Let's look at a config file. Sinclair?
Thank you, Cameron. So this config file, this is what the configuration will look after the process to make a connection is successful in our connection manager on the client's machine. The private key here was generated in a connection manager and is returned to the client after receiving a response from one of the VPS. The peer here is the server. The client will make a direct connection towards, and we need both the public key of the server and a full IP address and port number to make a connection on the client side. And let's take the next picture. This is an image of one of our server WireGuard instances running on a Docker container. They look pretty much the same. A lot of information is similar to the previous slide, but in reverse. The peer here is a client who has the sole connection to this container. The time between each handshake is calculated upon connecting to an interface and resets every few minutes. We can also see the information that was being transferred and received by the packet. The port number is randomly chosen for each container. And I'll pass on to...
I'll take it again.
Okay, cool.
So in the future, we were hoping to implement some form of load balancing for the connection manager to remove single point of entry. At the moment, we're just, we have our connection manager deployed on Heroku, and there's just one endpoint to hit. We also want to diversify the idea of permissions on a company so that they can provide more, we could provide more features with that. We are currently allowing you to have connections to very specific servers, but there's many more things that we can do with this feature. And we want to implement some form of Kubernetes orchestration for handling the scaling of the servers. Over the course of the project, we learned the value of developing a strong architecture, but we also learned that it had to be flexible to be reactive to change. We had to modify our architecture around 3 times, but we made sure to sit down and really discuss what we needed to change to minimize discourse in the future. We had developed a strong tool set for being productive in a remote working environment. I'm sure everyone in all of these groups will say the same thing. And we developed a strong understanding in Linux networking and Docker networking. We want to close this presentation off by offering special thanks to our sponsors, Kyle, Greg, Adrian, Brian, and Leo. Without their guidance, we would probably still be working on planning out our initial architecture. We also want to thank the professor and our TA, Arindam. Everyone here helped us achieve everything we have to show you today, and we're very grateful. Any questions?
Okay, so unfortunately we won't have much time for questions, but if you do have any, please see the team during their poster session, and I'm sure they will be happy to talk to you. So after the